everyone. We're going to start section 4.3, which is called Trigonometry Extended, the circular functions. Makes it sound kind of complicated, but it's not too bad. We're probably going to end up breaking this section into a couple of video segments just because there's so much information within the section. It's not going to be as long as one of the sections, and I think it was 1.2 in chapter 1, but we want to make sure that we take some time and go through each of the concepts for understanding. So we're going to start off with a definition, something called coterminal angles. So you need to think about the fact that you have two angles, one called alpha and one called beta, and these are considered to be what are called coterminal angles if, when we plot these angles on a coordinate plane, so we're dealing with plotting them on an x and a y axis, they share the same initial and terminal sides but have different measures. So I want you to think about that scenario for a second. We plot two angles on a coordinate plane. So let's draw our coordinate plane. And these two angles, alpha and beta, we could call them any other two names as well, but they share the same initial and terminal sides. So if I draw an angle, remember standard position has initial side along the positive x-axis, and I'll put the terminal side in quadrant 2. It looks like it's bisecting quadrant 2, so I'm going to call this angle alpha, which will say alpha is equal to 135 degrees. It looks roughly accurate. Now, for every positive angle that we draw, we also have a negative counterpart. So I could have gone and named this angle in this direction, the negative direction. We'll call this beta. And the measurement for beta would be, if this is 90 degrees, the negative y-axis, the negative x-axis would be 180, and then we went another 45 degrees, so this would be negative 225 degrees. These two angles are considered to be coterminal because they have different measures, alpha being 135, beta being negative 225, but they share the exact same initial and terminal sides. So here's a visual of exactly what's going on. Algebraically, here's what you need to think. Angles are coterminal. So angles are coterminal. Get this in your notes. When they differ by an integer multiple of 360 degrees or 2 pi radians. That means that if we were to subtract these two angles, the difference between the two angles would be a multiple of 360 degrees, or if we were working in radian measure, 2 pi radians. So let's test out that theory. If I take my alpha, 135 degrees, and from that I subtract negative 225 degrees, whoops, negative 225 degrees, we end up with 360 degrees. So that's obviously one integer multiple of 360. Even if I went in the other direction, negative 225 degrees minus 135 degrees, that will give us negative 360. That's still an integer multiple of 360 degrees. So they'll always differ by either 360 degrees, 720 degrees, 1080 degrees, so on and so forth, or their negative counterparts if you were doing it in the reverse order. So important to know that we have these things called coterminal angles, and coterminal angles differ by integer multiples of 360 degrees or 2 pi radians, and that they're sharing the same initial and terminal sides when we draw them. So we're going to try a few examples that deal with this idea of coterminal angles. I'm asking you to find a positive and a negative angle that is coterminal with the angle that's given to you. So we're going to start off with 30 degrees. 30 degrees, if I want another angle that's coterminal with 30 degrees, that means that another positive angle, it's got to be an integer multiple of 30 degrees, integer multiple of 360 degrees in relation to the 30 degrees. So I strictly could do this. 30 degrees, we're going to add another 360 degrees. What that means is I've gone where 30 degrees stands for on the coordinate plane, and I've gone one full revolution around, which means I'm now at 300, whoops, what am I doing here? Talking but can't write here. 380 90 degrees. So an angle of 30 degrees, if I draw this quickly and roughly, whoops, having trouble. X, Y, here's my 30-degree angle. Okay, if that's 30 degrees in there. If I were to have gone another 360, like if I had gone 360 degrees around from where that terminal side was, so back again, that would be a total angle of 390 degrees, which means I fall in the same spot. So this is a positive angle measure that's coterminal with 30 degrees. In order to find a negative angle measure, I would start off with the 30 degrees, and this time just subtract 360 degrees from it. So that would bring me to negative 330 degrees. An angle that measures negative 330 degrees has the exact same initial and terminal sides as an angle of positive 30 degrees. And you could draw that out to kind of test the idea. If I had gone in this direction, this would be negative 330 degrees. You know what? I don't want to use 150 here. I had changed my mind and I never changed it in the thing here. Let's put negative 470 degrees. So if we're starting with negative 470 degrees, I want a positive coterminal angle, which means negative 470 plus 360 is only going to get me to negative 110 degrees. So one revolution around, one integer multiple of 360 brings me to a negative coterminal angle. I could accept this for the negative part of my answer if I wanted to. But if I add another 360, so I'm going to continue on adding 360s, multiples of 360, until I get to a positive angle, I would get 250 degrees. So an angle of 250 degrees shares the exact same initial and terminal sides as an angle that would measure negative 470 degrees. I could take negative 110 as the negative angle here as well. If I wanted to go in the other direction, I could subtract 360 from negative 470 and I would end up with negative 830 degrees. So hopefully you're seeing here that there are multiple answers that are acceptable for something like this. Let's work in terms of radians too. I don't want you to try to convert. I want you to actually try to work in terms of radian measures. So if 2 pi over 3 is our radian measure, and I want another positive coterminal angle. Just since this is positive already, I want to guarantee that I have a positive. I'm going to add one revolution on. So if I add 2 pi over 3 plus 2 pi, I need a common denominator. 2 pi over 3 plus, this is 6 pi over 3, which leaves us with 8 pi over 3. So 8 pi over 3 is another positive coterminal angle. If I want a negative 2 pi over 3, I'm going to subtract the equivalent of 6 pi over 3 from that, and we'll end up with negative 4 pi over 3 as a negative coterminal angle. Negative 37 pi over 6. If we go from here, negative 37 pi over 6. If I want to get a positive angle measure, I'm going to add how many sixths? The equivalent of 2 pi. So we're going to have to add 12 pi over 6 onto this, which means one group of 12 pi over 6 is not going to quite cut it here. So that would bring us to negative 25 pi over 6. And in all reality, I need still quite a few more. If I add another 12 pi over 6, that's going to only bring me to negative 13 pi over 6. Another 12 pi over 6 is going to bring me to negative pi over 6. So I have to add 3 more groups of 12 pi over 6 onto this to get in the positive realm of things. So that's adding 36 pi over 6. If I add 36 pi onto negative 25 pi, that's going to bring me to 11 pi over 6. Double check my addition there because I'm kind of rambling on and not really checking to make sure if I'm adding correctly. So there may be an error there. A negative answer, again, I found a negative answer as I went through my work here. Negative 25 pi over 6 would be acceptable. Negative 13 pi over 6 would be acceptable for a negative angle measure. So hopefully you're picking up on the idea. You're adding multiples of 360 degrees or 2 pi onto or subtracting from the angle measure that's given. So please make sure that you're writing down questions. I know you're really good at doing that and taking good notes on these so that we can talk about anything that you might have concerns about in class when you get in the next time I see you. All right, we're going to shift gears a little bit. So that's one definition, coterminal angles. Now we're going to look at how the trig functions relate to the point xy on the coordinate plane. So we know how to plot a point xy. Now we're going to relate trig functions to these points. The first little blurb here says, let point P, which holds the coordinates xy, be a point in quadrant 1. And let R be the distance between P and the origin. So I want you to picture this. I want you to think about the drawing that would go along with this. P is a point in quadrant 1. So I've got to draw a coordinate plane, and I want you to do the same in your notes. P, here's point P, in quadrant 1, and let R be the distance from P out to the origin. So that means that from the origin out to point P, this is R. So it's the distance between the origin and point P. Remember, point P holds the coordinates x comma y. Now, you may have developed a little bit of this in geometry class way back when here, but if I were to drop an altitude from point P down to the positive x-axis, what I've done is I've created a right triangle. So that right triangle has legs that measure x units long for the base leg and then y units long for the height or the altitude of that triangle. So we kind of have a Pythagorean theorem relationship going on here. We also have a connection between where the coordinates of point P come from. It's x units to the right and y units up. Now, if this right triangle is formed, remember what we studied in the last section. If I call this angle theta, this central angle theta here, you know, with initial side here, terminal side here, and I've got this right triangle, I know according to right triangle trigonometry that the sine of theta, this is where I'm looking right now, it says use the acute angle definition of the sine function to prove that the sine of theta is equal to the value of y over r. Remember, sine is the same as opposite over hypotenuse. So look at this triangle. The opposite side of angle theta is y, and the hypotenuse is r. So we can say, based on this point idea, point P, that sine of theta is actually equal to the value of y over the value of r. Let's do that for cosine. Look at the same picture. Cosine, we know, is adjacent over hypotenuse. So that means that the cosine of theta, according to point P, is equal to, here's my adjacent, x over r. So it's equal to x over r. And tangent of theta, remember, is opposite over adjacent according to right triangle trig. So the side opposite theta is y. The side adjacent to theta is x, so y over x. I really could write this too then. If y is in the numerator, then y is sine theta and x is cosine theta. So another way to look at tangent on top of this point idea is that tangent is equal to sine over cosine. So there's a little development of a point connection using point P and our connection to right triangle trig in order to create some definitions that we'll be able to use in the future. So I'm going to move on to the next screen where we're going to write down all these definitions. This next screen will be an important place in your notes for reference as we start some of these problems. What this says here is, so if we know that theta is in standard position, that means that the vertex of our angle is at the origin and our initial side is on the positive x-axis, and point P lies on the terminal side of theta except the origin. R can represent the distance from the origin out to point P. So that's kind of what we just drew over there. We can represent the 6 trigonometric functions with this information as well. And we just developed the first 3. We said that sine is equal to y over r, cosine is equal to x over r, and tangent is equal to y over x. Here I have to make sure that I say that x can't be equal to 0. I don't have to worry about it in the first 2 parts of the definition because r, remember, is a distance. If point P is not sitting on the origin, and that's what that's saying in the definition up here, we don't have to worry about r being 0 in that denominator. Now the other 3 trigonometric functions, remember, have connections to the first 3. Cosecant of theta is the reciprocal of sine. So that means cosecant based on a point definition is going to be equal to r over y. Y, remember, can't be 0. Secant will be r over x, so x can't be 0. And tangent will be equal to x over y, and y can't be 0 then. So these are very, very, very important that you have them in your notes. You're going to refer to them as you start going through these problems because you probably don't know them right off the bat. But you will be responsible for knowing and understanding the definitions. I will not supply you with those on any kind of assessment. So, make a connection to what we just did on the previous screen and write down any questions you might have. We're going to jump into an example here, and then we're going to talk about something called the unit circle. So this example says, let theta, using theta as our angle, be the acute angle. You notice all of our angles are acute angles right now, in standard position, so important information there, whose terminal side contains the point P, which has the coordinates 5, 3. Define the 6 trigonometric functions in this situation. So I want you to picture what's going on. I want you to draw yourself a visual. Trig is as much visual as it is algebraic here. So point P holds the coordinates 5, 3. You don't have to be accurate, just judge that 5, 3 might be out here. So this is point P and it holds the coordinates 5, 3. We want to, based on this idea, we want to define the 6 trigonometric functions based on this scenario. So we know this. We know that there's some angle that can be created, this is theta, that passes through this point. It's in standard position. So here's this point P, and this is angle theta. If I drop that altitude down, we would create that right triangle. I don't even need to do that now because I developed this idea based on the definitions we have had on the previous slide. So I could go right in and I could say that the sine of theta is going to be equal to y over r. I have a little bit of a problem though, because r is that distance out from the origin out to point P. So I have to figure out what r is before I even jump into putting my answers here. If I drop that altitude, maybe I should draw the picture rather than just kind of reasoning my way through there. I know that this distance is 5 because that's the x value, and this distance is 3. In order to find that value of r, we could use the Pythagorean theorem. So 5 squared plus 3 squared is equal to r squared. 25 plus 9 is 34, so r squared is equal to 34, and r will be the square root of 34. Now remember, it's technically positive or negative, but because we're dealing with distance here, we're just going to assume the positive value. So sine of theta will be equal to the y value over the r value, 3 over radical 34, which is 3 radical 34 over 34. The cosine of theta will be the x coordinate, 5 over radical 34 over that r value, which will be rationalized 5 radical 34 over 34. And tangent of theta is y over x, or 3 over 5. So there are the first 3 base trig functions, the ones that we developed from SOHCAHTOA first. Now in order to get the other 3, cosecant, remember, is the reciprocal of sine. Remember, also write the angle measure that comes after the trig function. That will be equal to, I'm going to go back to this step to take the reciprocal rather than my final step so I don't have to re-rationalize, radical 34 over 3. Secant theta will be radical 34 over 5, again going to the first place where I got the answer, and then cotangent theta will be 5/3. So you notice that just knowing a point and knowing that the terminal side of an angle, an acute angle passes through that point P, I'm able to find that distance R, and I'm also able to find the 6 trig ratios for the situation that's described. Now, what I'm going to kind of do as a little sidebar here is talk about this thing called a unit circle. The unit circle is a circle that has a radius of 1. So if we were to draw it superimposed on a coordinate plane, not very good at drawing circles very accurately. That's not too bad. But the distance from the center out to any point on the circle is r equals 1. So that means technically that if I'm dealing with this point P that we were just talking about in the previous problems and the definitions, we could actually say, because the value of r becomes 1 in our definition, that the point value and the coordinates can be related to cosine theta comma sine theta, because technically the definition would become cosine theta would really be x over 1, sine theta would be y over 1. So instead of having y and x, since this is just x and that's just y, I can take my trig functions and put them in as coordinates. So cosine goes with x, sine goes with y. The way that I remember them is, I think, alphabetically. C comes before s, c comes before s, therefore x comes before y. So cosine and x go together and sine and y go together. So if you have a unit circle, then in a unit circle situation, cosine is equal to the x coordinate, sine is equal to the y coordinate. You don't even have to bring the radius into play because it's equal to 1. So we're going to rely pretty heavily on this idea of the unit circle with some of our work in the future, just because it makes things a little bit easier. So important, even though it was a quick little thing that I talked about here, we need to make sure that everyone understands. So if there are any questions on that, please make sure that you write them down and bring them into class. Another definition here on the next screen. It's called a reference triangle. It's kind of long. We'll talk about it and make some sense about it because it's going to help us as we start to move around the coordinate plane. I don't know if anyone, as I've been going through this, was thinking, well, every angle that you've kind of talked about has been within this first quadrant. But as soon as we move out of the first quadrant, our angles aren't acute anymore. Our angles become obtuse. So how do we deal with obtuse angles and the 6 trigonometric functions? We're going to use something called a reference triangle to help us within this section. What this says is, for an angle theta, so we've got our angle theta in standard position, the reference triangle is the triangle formed by the terminal side of angle theta, the x-axis, and a perpendicular drawn from a point on the terminal side to the x-axis. There's a lot of words there, and I'll go through a picture with you to help you understand. The angle in the reference triangle, this is an important sentence, the angle in the reference triangle at the origin is considered to be the reference angle. And this is the angle we're going to use to equate to the obtuse angle in the example. So what's going on here is we've got this angle in a problem, and this angle happens to fall, we'll put it in the third quadrant. So it's an obtuse angle, falls in the third quadrant, this is theta. Now, what we do to create a reference triangle is we pick some point on the terminal side right here. We're going to call that our point P, for example, like we did before, and we're going to create a perpendicular drawn from the point on the terminal side to the horizontal axis. So this time it's like we're raising an altitude and we're creating a right triangle here. So this little triangle that's created has an angle theta, a central angle theta there, that we're going to use in order to calculate the 6 trig functions of this big obtuse angle. All of the ratios for the 6 trig functions can be based right out of that little reference triangle and correspond to that big obtuse angle that is drawn in the third quadrant. So crucial to understand what's going on because this is going to help us deal with all those angles that fall outside of the first quadrant. So I'm going to do an example with you here for 315 degrees. Forget about part B for a second here, so I can just kind of enlarge. I don't have a lot of space on the board, so we'll do the 315 degrees and then I'll move on and do the next one in radian measures. So an angle of 315 degrees kind of looks like the one I just drew. We have our initial side here, and our terminal side 315 degrees is actually going to fall, though this time in quadrant 4. So 315 degrees. That's theta. I'm going to pick a point on the terminal side, and I'm going to create a perpendicular to the horizontal axis, which now gives me this reference triangle right here. This little angle in here, which I'll call alpha, is now our reference angle. Alpha is the reference angle. And what that reference angle is going to do is going to allow us to evaluate the 6 trig ratios of 315 degrees. We should be able to figure out what the reference angle measure is based on where this big angle, obtuse angle, falls in the coordinate plane. And sure enough, since we know that the big angle is 315 degrees, alpha is equal to 45 degrees. So what we've basically done is create a 45-45 right triangle. I'm going to kind of blow that up a little bit right here. So this is 45 degrees. That's the value of alpha. This is 45 degrees. That's the value of alpha. And now if I can figure out the ratios of that triangle, I'll also know the ratios of 315 degrees. So to help us out a little bit, I'm going to force the situation of having the hypotenuse equal to 1. And I think we talked in class that the leg values then would be radical 2 over 2. This time, this would be negative because it's falling in the negative y-axis. And then this would be a positive radical 2 over 2 up here. So we've got this triangle, 45-45 right triangle. It has legs of radical 2 over 2 and negative radical 2 over 2. And we know that it's a reference angle that corresponds to theta equaling 315 degrees. If I want to find the 6 trig ratios, that means that this point, which I can call point P, holds the coordinates radical 2 over 2, comma, negative radical 2 over 2. And I know that the R value is equal to 1 because I forced that situation in my triangle over here. So if I erase a spot right here, I'm able to tell you then that the sine of 315 degrees through the reference angle, 45 degrees falling in the 4th quadrant, is equal to the y-coordinate of negative radical 2 over 2. The cosine of 315 degrees is equal to positive radical 2 over 2, the x-coordinate. The tangent of 315 degrees is equal to negative 1. That's the y-coordinate over the x-coordinate. And then cosecant of 315 degrees is going to be the reciprocal of radical 2 over 2. So if I flip that, 2 over radical 2, it's negative. And I rationalize radical 2 over radical 2, I get 2 radical 2 over 2 is negative, which is just negative radical 2. So this value is negative radical 2. The secant of 315 degrees is going to hold the same value, but it's going to be positive. And the cotangent of 315 degrees is going to be negative 1 because it's the reciprocal of the tangent function. So our 6 trig functions have been found based on what we consider to be a reference triangle. We did something out of the 1st quadrant. We found the reference triangle. We found the reference angle. We made a connection with that reference angle and created our ratios for a 45-45 right triangle using a hypotenuse of 1. So we could use that definition of P. And then we're able to use, the definitions that we just developed in the other screen in order to determine the 6 trig ratios. I think I'm actually going to stop there. We'll do the radian measure one in the other video, or we'll pick up with that one in class in case you have questions on that. I think this is enough for the time being. There was a lot of information in there for you to digest, and we'll make sure that we take questions on it and do a little work together in class before we move forward with anything else. But maybe, you know what? here's what I'll leave you with. For the end of the video, why don't you try this one, 7 pi over 6, and see what you come up with. And then that will be the first thing that we talk about together in class. So rather than having me just do it out in class or do it on another video, you try doing 7 pi over 6 before you come into class this for the next class period. Okay, lots to digest there. Thanks for listening, and I will see you soon.